Okay, hello everyone. Today we'll learn about the sampling distributions and the central limit theorem part 2. Okay. And now let's learn about the central limit theorem. Suppose y1, y2, and yn is a random sample from any distribution with mean mu and variance sigma square. Okay, and what we know, what we can learn about the population. Actually, we know that expected value of y bar is mu, and variance of y bar is sigma squared divided by n. And actually, we can still do the inference about the population with y bar. What is it? And actually, the y bar follows normal distribution as sample size n goes large. This result is called the central limit theorem. So this is very interesting. The y1 to yn, they are from any distribution. However, if when the n goes large, their sample mean follows the normal distribution. And this is the definition of the central limit theorem, and we will learn about this central limit theorem using simulation and also theoretical proof as well. Okay. Let's look at the example. Suppose y1, y2, and yn is a random sample from exponential distribution. So y1 to yn follows this exponential distribution. Here's density function and graph of density function. And then if we calculate sample mean of n equals 5. So we take random sample, 5 number of random samples, y1 to y5, and calculate mean of that y bar, and we calculate y bar 1000 times and make the histogram. Then the histogram looks like this. The distribution of y bar looks a little bit normal, and this is actually when the sample size n equals 5, and if we increase the n, if we increase n equals 25, what it means is that we randomly sample 25 samples, like we y1 to y25. We get this, and then we calculate y bar from 25 samples, and we calculate y bar 1000 times and make the histogram of that y bar. Then the result looks like this. This looks much more looks like more normal than the previous example. So this is the simulation result that of the central limit theorem. As we learned from the central limit theorem, y1 to yn follows any distribution. In this case, that any distribution is exponential distribution, and as n goes large, the distribution of y bar follows normal distribution as n goes large. N equals 5 is this case, and n equals 25 is this case. Here is more rigorous definition of the central limit theorem, which is Theorem 7.4. Let y1, y2, and yn be independent and identically distributed random variables with expected value of yi equals mu and variance of yi equals sigma square, which is less than infinity. And let's define un this way, and it's a function of y bar, and y bar is the average of yi's. And then the distribution of function of un converges to the standard normal distribution function as n goes to infinity. That is this thing. And actually, as you can see, if y bar minus mu divided by sigma over square root n follows normal, standardized normal, And actually you can check that y bar follows normal with mean mu and variance sigma square over n. Yeah, so they are the same story, so you can check this. Okay, let's learn about the example 7.9. The service time for customers coming through a checkout counter in a retail store are independent random variables with mean 1.5 minutes and variance of 1. Approximate the probability that 100 customers can be served in less than 2 hours of total service time. Okay, so we are interested in the service time of 100 customers. So for each service time y, the expected service time, let y as a service time with time for a customer. Um, and EY is 1.5 minute and variance of Y is 1.0. And actually we have 100 customers. So we have 100 customers. I equals 1 to 100. And we want to this is served less than 2 hours. Less than 2 hours. 120 minutes. So we want to calculate this. And what we know is that the y bar, the mean service time would follow the normal distribution with 1.5 minute and variance is 1 over square root of n, n actually. 100. And so y bar minus 1.5 divided by 1 over 10 would follow normal distribution 0, 1. This is standardized normal distribution. And so to calculate this, we can write it as probability of we should divide it by 100 and so this is y bar minus 1.5 and here 1.2 minus 1.5 and we divide it by 1 over 10 which is 10 times of this and 10 times of this. And so this is the probability of and actually it approximation. We can use normal approximation by central limit theorem by CRT. It is minus 0.3, minus 3. So minus 3. Okay, and this is normal distribution, and from normal distribution table you can calculate this probability. The probability is 0.0013. Okay, so you can apply central limit theorem and solve the problem like this. Okay, let's move on to exercise problem 7.57. 25 heat lamps are connected in a greenhouse so that when one lamp fails, another takes over immediately. Only one lamp is turned on at any time. The lamps operate independently and each has a mean life of 50 hours and standard deviation of 4 hours. Okay, each lamp has mean life of 50 hour and standard deviation 4 hour. In the greenhouse is not checked for 1,300 hours after the lamp system is turned on. What is the probability that a lamp will be burning at the end of the 1,300 hour period? Okay, so we want to find the probability of um, lamp will burning after 1,300 hours. And actually, here 25 heat lamps are connected. So yi 25 I equals 1 to 25. 25 heat lamps are connected, and expected value of yi for each lamp, so expected value is 50, and variance of yi is 4 square. Okay, so what can we tell about y bar by CRT? Y bar follows normal distribution with mean 50, and variance is divided by 25. And so what we know is y bar minus 50 divided by 4/5 follows normal distribution 0, 1. Okay, so what we going to do here? So here the probability of this 25 here, and so y bar minus 50 is 25 52. Okay, so 52 minus 50 and divide by 4 and 5, 4, 5. And that is probability of z is greater than 2/4 times 5, which is 2.5. Okay, so this becomes probability of standard normal z is greater than or equal to 2.5, and if you use the standard normal table to calculate this value, you will find that this is 0.0062. Okay. And homework for chapter 7.3 are these 7.42 and 7.43. Chapter 7.4 is a proof of the central limit theorem. Okay, so this is time to solve why the central limit theorem is true. We were going to use theorem 7.5. Let's look at what it is. In theorem 7.5, let y and y1, y2, y3, be random variables with moment generating functions mt and m1t, m2t, m3t. They are respectively, and if the moment generating functions m and t, the limiting distribution of m and t as n goes to infinity is empty for all real t, then the distribution function of yn converges to the distribution function of y as n goes to infinity. We are not prove the theorem 7.5 itself. Actually, we were going to admit this theorem holds, and actually the theoretical derivation of this thing is a little bit tricky for undergraduate level. So now we will just admit this theorem will hold, and we were going to use this theorem to solve the central limit theorem. Suppose y1, y2, and yn is a random sample from any distribution with mean mu and variance sigma square. Then the y bar minus mu divided by sigma over square root of n follows normal distribution, a standardized normal distribution. This is the definition of the central limit theorem. And to prove this, let's define un as this. So our un is this, and actually we can represent this notation as this. Sum of yi minus n mu, and actually this is the y bar. It is sum of yi's divided by n, and so you can get n down here, and then you get this notation. And also you can represent this notation with this one. And here, after getting this notation, you let zi as this thing. You let zi as yi minus mu divided by sigma. And what you know is that expected value of zi, because the mean of yi is mu, and the variance of yi is sigma, the expected value of zi is 0, variance of zi is 1. And the moment generating function of sum of zi's, the moment generating function of sum of zi's can be written as this. The moment generating function of z1t times moment generating function of z2t times dot 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 moment generating function of z and t. And actually, the all zi's are independent and identically distributed. You can write it as moment generating function of z1t to the n. Okay. So we have this, and for a moment generating function of u and t, and actually we know that u and t, un is the 1 over square root of n, sum of I equals 1 to n, zi. So we know this, and from here we can get this one. So this one is expected value of e to the unt, and actually this is e to the 1 over square root of n, sum of zi t, and we can put 1 over square root n with t, so we can write it this way. And here, since all the zi's are independent, you can write it as e to the expected value of z1 t over square root of n to the nth. So this is here. Okay. And by using Taylor theorem for mz1t, you can express mz1t as this one. This is Taylor theorem at point 0, and from here, let's calculate these values, and actually this is 1 because expected value of e to the 0 is 1, and this is expected value of z1. This is actually expected value of z1, which is 0, and this is expected value of z1 squared, which is variance of z1, and this is 1. So you get this. So you get 1 plus 1 over 2 t squared plus big O notation with t third. So here's t third, and this big O notation implies that this is depends on t third term. That's notation like that, and the computational complexity is depends on t third. Okay, and if you put this mzi1t inside of here, you get this. So munt is mz1 t over square root over n to the nth, and if we put this mz1t here, we get this. And so now we need to get the limiting distribution of this term. One of the easiest way to find this limit is using this definition, like limit as n goes to infinity, 1 plus 1 over n to the n. This converges to e. This is definition of e, and how we can use it. And actually, this term, this term, uh, this term goes to 0 faster than this term, so it becomes negligible. So this term goes to 0 faster. So we calculate limit n goes to infinity, 1 plus t squared divide by 2n and nth. And from here, actually this, for this term, we can rewrite this as 1 plus t squared 2n 1 t squared 2n and times 2 to t squared. So we can represent this term as this, and n goes to infinity. And also we can, as n goes to infinity, that means 2n divided by t squared goes to infinity. So the term here converges to e. So this becomes e to the t squared divided by 2. And this is the moment generating function for standard normal distribution. So as what we know is that limiting distribution n goes to infinity, mun t goes to the e to the t squared divided by 2, and this is moment generating function for standardized normal mgf of standardized normal. So this is the proof of the central limit theorem. Chapter 7.5 is the normal approximation to the binomial distribution. Um, uh, Central limit theorem can be used to approximate probabilities when the exact probabilities are tedious to calculate. This situation is for the binomial distribution. So in binomial distribution, we can usually calculate it using exact distribution, exact probability distribution. However, the calculating each probabilities, it's time consuming. So if our random variable y follows binomial distribution with n and p, and as n goes large, the calculating the exact distribution, there are too many cases, and using central limit theorem, we can get a nice approximation of this binomial distribution. We're going to learn about this in this chapter. So suppose y has a binomial distribution with n trials and probability of success p. We can think of n number of Bernoulli trials xi with success probability p, and then our binomial random variable y can be expressed as this. Sum of Bernoulli trials is following binomial distribution. So we can write it this way, and so this is sum of random variables. And so as n goes large, we can apply central limit theorem. So y over n, which is x bar, and we know the expected value of x bar and variance of x bar, and so by using CLT, central limit theorem, as n goes large, we know the x bar follows normal distribution like this. Okay, let's move on to example 7.10. Candidate A believes that she can win a city election if she can earn at least 55% of the vote in precinct 1. She also believes that about 50% of the city's voters favor her. If any 100 voters show up to vote at precinct 1, what is the probability that candidate 8A will receive at least 55% of their votes? Okay, the probability, we want to find the probability of 100 voters, and each vote it follows Bernoulli trial. Let's define it BI. BI follows Bernoulli distribution with P, which is 0.5, about, and we have 100 voters, and we want 100 we want to find the probability of this exceed 0.555. Okay, and how can we apply central limit theorem? The sum of random variable is a sum of BIs, and the mean of BIs, which is let's say this is B bar, and this one by CRT, the B bar is actually sum of BIs equals 1 to 100 divided by 100. And this one follows normal distribution with probability P 0.5, and the variance is P1 minus P divided by N. So the variance term is 100 here, 0.5 times 0.5. Okay, so let's use this from here. Okay, so probability of b bar minus 0.5 divide by square root of square root of uh, 0.5 times 0.5 divide by 100. And actually, is square root of this thing is actually 10 over zero point 0.5. Okay, so 0.55 minus 0.5 divided by 0.5 divided by 10. Okay, and so this probability, we can approximate this term as z. Uh, and this part becomes 0.05, and here this part 5, and this is probability of z is greater than 1. And from the normal table, the probability of standardized normal distribution is greater than 1 is 0.1587. Okay, so this is the proof using Bernoulli distribution and central limit theorem. Okay. Let's move on to example 7.11. Suppose that y has a binomial distribution with n equals 25 and p equals 0.4. Find the exact probabilities that y is less than or equal to 8 and y is equal to 8, and compare these to the corresponding values found by using the normal approximation using CLT, central limit theorem. Okay, and for the probability of y is less than or equal to 8, you can directly prove it using the binomial distribution table. So y follows binomial distribution with n equals 25 and p equals 0.4. And also this is the y is actually sum of Bernoulli trials, BIs. So you can use the central limit theorem, 25 number of Bernoulli trials. And to approximate it using the normal, the probability of y is less than or equal to 8 can be approximated as probability of w is less than or equal to 8.5. And actually this w is approximation of y. So in the figure 7.9, the rectangular bars are densities from the binomial distribution, and so the probability of y is less than or equal to 8 is sum of these rectangles. And to estimate these blue areas, what we can do is, rather than summing up all these rectangles, we can actually get the integrated value. We can actually calculate this purple area, which is approximated by the normal curve, and the purple curve to the 8.5. So that's why we calculate the probability of w is less than or equal to 8.5. Okay, and for the normal approximation, since this since this y y is actually sum of binomials, and for each bi, the probability of bi is bi equals 1 is 0.4, and so sum of bi uh, yeah, have mean of y is np, and variance of y is np 1 minus p. So the w is going to follow normal distribution with mean np and the variance np 1 minus p. So that's why we normalize it this way, and um, after this normalization, it summarizes as probability of z is less than or equal to minus 0.61, and which is 0.2709. And as we can compare these two numbers, we can see that when n equals 25, the probability of y is less than or equal to 8, they look very similar. The approximation works very good. Okay, then how can we calculate this y equals 8? To compare the probability of y equals 8, the probability of y equals 8 is can be directly calculated from the binomial distribution table, and the probability is 0.120. And the probability of this thing is actually this rectangle area, and this rectangle area can be approximated as integrating w from 7.5 to 8.5. So this red rectangle actually can be approximated by integrating the normal curve from 7.5 to 8.5, and this is how we can approximate. And I will skip the detailed calculation for this case, and you guys can try by yourself and compare the value calculated from normal approximation to this thing, and they should be very similar, and also written in the textbook. Homework for chapter 7.5 is this one homework. And thank you very much. This is end of the courses for the week 1. And yeah, nice to meet you all again. And let's also enjoy our semester. Okay, thank you.